evening. Welcome to this webinar by Lottie Thomas. She works for Mirada and she's going to be doing a talk on DLCExpert, improving patient outcomes in radiotherapy using deep learning. My name is Eunice Basin. I'm one of the committee members. I represent young people, so I do encourage young people to join our committee. And I just want to tell you also about another talk we've got next month. That is on the 20th of May 2021 between 7:30 and 9, and it's called The Rise of Moral Machines, and that will be next month. I hope you can join us in that particular talk as well. Lottie's going to talk about radiotherapy, and it's about how we're going to be talking about how machine learning can be used in terms of diagnosing cancer. Cancer is something that we all feel very passionate about, and we hope that one day we can solve the problem of cancer. So without further ado, can I please welcome Lottie, and thank you very much for joining us.
Thanks, Janice, and thanks everybody for joining the presentation this evening. So tonight I'm going to be exploring how AI can be used to improve medical treatment, specifically using deep learning to improve patient outcomes in radiotherapy. So my name is Lottie Thomas. I'm a principal software architect at Mirada Medical. I'm the development lead for our products in our deep learning radiation oncology segment. I joined Mirada in 2018, so I've been there for about 2.5 years now. I actually originally trained as an audio engineer, but I moved into software development, and I've recently completed a master's in software engineering at the University of Oxford. Mirada is an imaging software company based in Oxford. We specialise in imaging for cancer treatment. We were founded in 1999 as a spin-out from Oxford University, and now have a wide range of imaging products for cancer diagnosis, radiotherapy, and interventional treatments. In 2018, we released the world's first deep learning powered product for radiation oncology, and in 2020, we won a UK government grant to deliver AI to the NHS. Our main office is in Oxford, but we also have offices in Denver in Colorado, and another in Bordeaux in France, and we also have remote colleagues all around the world. In this talk, I'm going to explore the benefits of using AI in medicine, specifically cancer care, and talk about how we are using deep learning to improve patient outcomes in radiotherapy through our software called DLCExpert. So let's start talking about AI in healthcare. First, I'll talk generally about the increasing use of AI in healthcare, its potential applications, and the challenges in making it a reality. So artificial intelligence is a broad definition for any technique that allows a computer to carry out a task in a way that we would consider smart. It encompasses a lot of what we expect software to do, using logic, if-else branching, decision trees, but AI is often thought of in the context of machine learning. Machine learning is a subset of AI, in which the computer is trained to perform a task without being explicitly programmed to do so. For example, learning the preferences of a specific user, and then recommending them similar items like we see in shopping programs, music, films. A specific type of machine learning is called deep learning. Deep learning uses deep neural networks to create a hierarchy of features in data. What's special about deep learning compared to the broader machine learning definition is that the algorithm identifies important features in the data itself without a human needing to provide any pointers. The algorithm therefore identifies compositions that humans couldn't, and it results in some very effective training. So there's a growing interest in AI techniques in the healthcare sector. There's a quote here from the Chief Executive of the NHS, Simon Stevens, in 2019. He said, "We are seeing an artificial intelligence revolution that will be a big part of our future over the next 5 years, with technologies that can cut the time patients wait for scan results and ease the burden on hardworking NHS staff." In the same year, Matt Hancock, the Secretary of State for Health, announced a £250 million investment in AI research and technology in the NHS. As part of that announcement, he said, "We are on the cusp of a huge health tech revolution that could transform patient experience by making the NHS a truly predictive, preventive, and personalised health and care service." We've seen a sharp increase in recent years in the number of publications that apply AI to healthcare. So this graph is looking at the number of articles that have been published that mention AI and radiology. Radiology relates to patient scans. The different colours in this chart are the different types of scans that are used. So we've seen that the number of publications increased 9 times in 10 years, from 100 publications in 2007 to 900 in 2017. This is also reflected in the number of algorithms using AI that have been approved by the Food and Drug Administration, who are the regulatory body in the United States. In 2014, they approved just 1 algorithm using AI, and in 2018, they approved 25. The algorithms they approved cover a range of areas, but most of them fall into radiology, so patient scans, and cardiology, which relates to hearts. So let's have a think about the example where AI is being applied in the healthcare service. So the first area is primary care services. Primary care services are the patient's first point of contact in the health service, such as their GP or their pharmacy. Babylon is an example of a company in this space. They have a few services. On the left here, they have an AI system in the form of a chatbot that asks the patients about their symptoms, compares the information they've given to a database, identifies matches, and then suggests a course of action. Seeing your GP, speak to your pharmacist. They also offer a health check service, which takes information about the patient's lifestyle and family history and generates the reports and insights to help them stay healthy. Another area where AI is being used is in screening for illnesses. The NHS runs a number of screening programs to detect early signs of illness. These programs generate a large amount of data that must be analysed, and AI is being used to reduce the workload of the specialists that analyse that data. So one example is Chiron, who are using AI to detect breast cancer on mammograms. Their product Mia is currently part of a trial within the NHS, looking at its impact on the NHS breast screening programme. Usually a breast scan is examined by 2 radiologists who determine if the patient needs further investigation based on what they see on the scan. In this trial, one of the radiologists is replaced by the software. Initial results are showing that Mia is able to predict breast cancer from the scans with the same performance as a human, meaning that it's viable for use in this way, and so potentially could halve the workload of the radiologists. It's important to note here that the AI is supporting the humans and not replacing them. And the power lies in reducing the workload of clinicians, allowing them to focus their time on tricky cases or spend more time with their patients, and for the screening service to expand in the future. And finally, AI is also being applied in treatment planning, which is where Mirada's DLCExpert falls. I'll also talk about this more in depth later. But it's a tool to improve the treatment a patient receives by assisting in the treatment plan. Contouring is a very time-consuming process, and deep learning has been shown to be a significant time saving over manually contouring and also over existing auto-contouring solutions. It speeds up the planning process and allows clinicians to focus on tricky cases, and again, for our services to expand. So we've seen that the increased interest in AI in healthcare is growing. We've also seen that research and technology are appearing to respond to it, but how do we get that used in the treatment of real patients? Delivering AI in healthcare poses a number of challenges. First, like all medical devices, it must be approved by safety regulators. And once we've got it approved, we then need to sell it to clinics. To do that, we have to overcome sort of the general fear of AI, and also managing the expectations of what it can achieve. So all medical devices must be approved by safety regulators, and that includes software. Most countries have their own regulatory body. In the UK, it's the MHRA, and in the US, it's the FDA. Each regulatory body has its own process and requirements, and you must get approval from each country that you want to sell the product in. Some areas have a group authority like the EU, which lets you cover a number of countries with a single approval. Regulators require proof that the product does what we say it will and that it's safe. And to do that, we provide evidence. And the amount of evidence that you need to provide depends on the claim of what the software does. A piece of software that claims to reduce the time taken for a clinician to do the task requires basic evidence, while a treatment that claims to save lives needs a significant amount of evidence, just like we've seen with the COVID vaccines. When it comes to AI, there's two questions often raised that relate to transparency. How can I know that what the software is doing is right? And why did it make that decision? So the correctness of an AI device is proven in the same way as any other device, through trials and clinical assessment, such as we've seen Taiwan performing with their breast cancer screening. We can also provide evidence for how a decision was made, such as showing the path through a decision tree in the Babylon chatbot. This can be more challenging for deep learning, where the decision is hidden inside the neural network and may have been made in a way a human doesn't quite understand. Another common question is about continuous learning. Some AI systems are able to continue to learn after they've been deployed. So for example, if the system is predicting tumors, we can later combine with the pathology report to see whether there was actually a tumor there or not. Feed this back to the AI and allow it to improve its predictions. This poses the question, how do we know that the software is still giving the right result? And the solution to this is frequent quality assurance. We test the software periodically to see if it's still providing a good result. This is actually no different to what happens with physical medical devices. A linear accelerator that's used to deliver radiotherapy is frequently tested to see if it's giving the amount of radiation that has been specified, and it's adjusted if necessary. We can do exactly the same thing with our AI. So despite the regulatory evidence, many people are still apprehensive about using AI in a clinical setting. Apprehension towards the growth of AI comes from concern about the care that might be received, and also, as it does in many sectors, about how it will affect people's jobs. For patients, the chief concern is in mistrust of the AI. They prefer to trust a human with years of experience over software, even if the software is proven to be effective. And for clinicians, they fear that the software will replace them and their skills, and they worry that embracing AI is putting themselves out of a job in the future. The solution to both these problems is careful education and marketing. Selling AI as a tool to aid clinicians shows they're not being replaced, and it allows patients to trust it, knowing that an experienced clinician is also on hand. We can also highlight the benefits. A clinician using AI to optimize their workflow has more time to spend on face-to-face care, and it allows us to expand services and treat more patients. And finally, once we've got our customers on board with our AI, education becomes important in managing their expectations of what it will achieve. Many people have an expectation of what AI does, maybe based on some basic knowledge, something they've read or seen. And these expectations can be beyond what we can achieve. So we need to be clear about the strengths and limitations. So for example, machine learning is limited to things that humans can label. We can train software to determine from a scan whether a tumor is malignant or not, because we have historical scans that can be combined with pathology reports. We can't train the software to pick something out on a scan, which we know labeled data for. If a human couldn't teach something, machine learning isn't able to learn it. Ultimately, what's required is for our marketing to be honest with our customers, managing the expectations of what AI can achieve instead of hyping them. So I've talked generally about AI and how it can be used in healthcare and the challenges of doing that. So I'll dive into a specific case of how we can improve radiotherapy using deep learning. To start, I'll talk about the challenges facing cancer treatment and give an overview of the radiotherapy process. I'll talk specifically about treatment planning and how deep learning can be used to improve it. Incidences of cancer are rising globally. In 2020, there were 19 million new cases of cancer worldwide. And this is predicted to rise to 29 million a year by 2040. That's an increase of 66% over 20 years. Cancer research estimates that half of us in the UK will develop cancer at some point in our lives. And that increase is largely driven by our increasing life expectancy due to our ability to treat other illnesses. That's quite a scary statistic, so it's worth noting that survival rates are also increasing, and 50% of cancer patients in the UK now live for at least 10 years after their diagnosis. As incident rates increase, the capacity of the healthcare system must also rise to meet the demand. A report commissioned by Cancer Research, again in 2014, showed that a key concern amongst NHS staff is a lack of resources and budget, meaning they were struggling to keep up with demand even 6 years ago. The Royal College of Radiographers and the British Institute for Radiology estimate that there's a shortfall of 6,000 radiologists and radiographers in the UK. And these professions are required for diagnostic scans and for providing treatment. Against this backdrop, we've got our target treatment timeline for cancer patients. The key milestone is 62 days from being referred by a GP to a first treatment. And within that, we've got 14 days between GP referral and being seen by a specialist, and 31 days from the decision on treatment to the treatment actually being delivered. Delays to this process impact the patient outcome. Cancer that's not treated promptly is likely to spread, which reduces the chance of survival, makes it harder to treat, and causes worsening symptoms. As we all know, COVID-19 has also added extra pressure to the NHS, and Macmillan, the cancer charity, estimate that there were 50,000 missing diagnoses over the past year. This is the shortfall between diagnoses they would expect to see and the number that have actually happened in the past year. This isn't diagnoses that don't exist. This is people with cancer who haven't yet been diagnosed, and it's highly likely that they will be eventually. This might be because they didn't come forwards to their GP, possibly because they're afraid of catching COVID or not wanting to further burden the NHS. And a report in The Lancet this week estimated that 45% of people with potential symptoms of cancer didn't contact their GP last year. Another reason that we have these misdiagnoses is possibly people who are waiting for a test. In December 2020, there were 1.3 million people waiting for one of the main diagnostic tests, which includes things like blood tests and scans. And there were 4.4 million fewer scans performed in April to September 2020 compared to the same period in 2019. This is a backlog that's going to need to be caught up, and those people affected by the delays are likely to need more care than they would have done had they been diagnosed earlier. So we can see that there's an increasing backlog of patients requiring cancer care, but a lack of resources and funding to match. We therefore need to look at how we can optimize the treatment process to maximize the resources we have and move patients through their treatment as quickly as possible. Radiotherapy is a treatment option for cancer that uses radiation, such as X-rays, to destroy the cancer cells by damaging their DNA and preventing them from dividing. Radiation can be delivered externally using a linear accelerator, as in this picture, or it can be applied internally, for example, by injecting a radioactive substance that's carried to the tumour by the bloodstream. About 50% of cancer patients will receive radiotherapy at some point, and it's often used alongside other treatments like surgery. So radiotherapy works by damaging cancer cells, but it also damages healthy cells that it comes in contact with. This causes side effects, which can vary in intensity and can sometimes cause permanent damage to organs. When planning radiotherapy, clinicians aim to reduce the amount of radiation healthy tissue receives, to minimize these side effects and lasting damage, without compromising on the dose received by the tumour and so the effectiveness of the treatment. Patients treated using radiotherapy usually go through roughly the same workflow from their treatment decision to the delivery of that treatment. So once radiotherapy has been chosen, the first step in the workflow is to do a simulation scan. Before delivering treatment, a dosimetrist needs to decide how much radiation to place where to achieve the prescription from the oncologist, while minimizing the effects on the surrounding healthy tissue. And to do this, they create a simulation of the patient on which they optimize their plan. And the first part of that is to take our simulation scan. So the simulation scan is a scan of the patient positioned exactly as they will be for their treatment. For example, breast cancer patients are usually positioned with their arms above their head. The scan is likely to be an MRI or a CT scan. CT is very common, and it's often combined with an MRI because MRI is able to get more detail of soft tissues. It's becoming more common for MRI to be used alone. A CT scan uses radiation to take the picture, but an MRI doesn't, so it's a much safer form of imaging that can be repeated more often, so it's becoming much more popular. A scan provides us with a three-dimensional internal view of a patient. This is an example of a CT scan covering the thoracic region, so this is from about the chin of the patient to the upper abdomen. So we've taken a 3D picture of the patient, but we want to view it on our screen, so we look at it in 2D slices. We can choose to view in the axial plane, which is the picture on the left. This picture is looking at the patient through their feet, so this is as if they were lying with their feet facing towards you. We can view in the coronal plane, which is the top, looking at the patient from their front, or we can view in the sagittal plane, which is viewing the patient from their side. And what we're seeing here is slices of the patient, and the slices add together to form the whole image. You could think of this a bit like a slice of bread, where the slices come together to form the whole loaf. We can view the scan by moving up and down the patient, front and back, left and right, so that we're able to see the whole image. And we can see a great deal of detail in these images of the patient. A CT is a map of density, and lighter colors represent more dense areas. So in this picture, we can clearly see the lungs are the dark area because they're full of air. The heart is in the middle. Here, this is the heart, and then the lighter areas are bones, so we can see some ribs and the spine at the bottom. The acronym CT actually stands for computed tomography. While it's quite an old technology, and this is a presentation about AI, I wanted to highlight CTs. They're a great example of where computers have revolutionized healthcare. Before CTs, it wasn't possible to view patients in the kind of detail that we see here. It was really only X-rays that were available. So the CT scan completely changed treatments like radiotherapy, allowing us to make much more personalized and much more precise treatments. And we're hoping that AI will have the same kind of impact. Once we've got our simulation scan of the patient, the next step is to identify the parts of the scan that are relevant to our treatment plan. And this is a process that's called contouring. What we're doing in contouring is identifying volumes within our three-dimensional image that represent the areas of interest and outlining them on our scan. There are two types of areas that are contoured. The target is the tumor, and the OARs are organs at risk. This is our healthy tissue that surrounds the treatment site that's at risk of receiving radiation. This is an example of some organs at risk contouring. This shows 5 contours. We've got the 2 lungs in blue, the heart is in red, and the yellow one is the esophagus, and the green one is the spinal cord. So as I said, CTs are viewed in slices, and what the clinician who's doing the contouring will do is they will take a slice and outline the organs on that slice, and then move on to the next one and repeat the process and keep going through the patient until they've outlined everything they want to do. When you put the slices back together, you get a volume within the image that represents the organ, which provides us a 3-dimensional map of where the important regions are. This creates a digital model of the patient and the areas that are important for the treatment, which allows the clinicians to use software to optimize the plan for the patient. Once contours have been drawn, they are reviewed by another clinician. It could be one or more clinicians who do the reviewing. After review, they may be edited if there's disagreement, but once everybody's happy, they're approved and we move on to our treatment planning stage. Treatment planning is the process of deciding where to place beams of radiation and with what intensity in order to maximize the dose to the tumour and minimize the dose to the organs at risk. So the model that we've created using the scan and the contours is used to simulate exactly how much dose will be applied to each area of the patient. A dosimetrist will then tweak the plan, looking at different combinations, different options, to see what the optimal plan is to ensure we have the most effective treatment, but reducing side effects and ensuring that we minimize any sort of permanent damage. This is an example of an expected dose from a plan. On the right, there's a picture of a linear accelerator, which is what we use to deliver radiation. The patient lies on the bed here, and this head is able to rotate sort of completely 360 degrees around the patient. This lets us create some quite complex treatment patterns. So in this picture on the left, this is an example of a treatment plan. In this, the red area is a high dose of radiation, and the blue areas are a low dose, and the green is somewhere in between. So what this plan has been defined as is 9 different beams of radiation coming from different angles around the patient, which join together. They're delivered one at a time, but they sum together in the middle to make a high dose to where our tumour is, while ensuring a low dose to the surrounding healthy tissue. Once our plan's been created, it's again reviewed and approved, and then we can deliver our treatment. Radiotherapy is normally delivered in a number of fractions, so the patient will have a number of appointments at the clinic, maybe 1 a day for maybe 3 or 4 weeks. And at each appointment, a small portion of the dose is delivered over a number of days, over the 3 weeks, which add up at the end of the treatment to the total prescription that was given to them. One final part of the process to highlight is that sometimes during delivery, the anatomy of the patient will change. The tumour may reduce, the patient's organs may move, and the patient themselves may change shape, for example, by losing weight. In these cases, sometimes the treatment plan that was optimal at the start of treatment is no longer usable. Maybe we're over-treating because the tumour's reduced, or sometimes just treating completely the wrong place. We detect this by use of a fast scan that happens before each delivery of the treatment. So every day when they come in, a fast scan will be performed to see kind of how they are on the day. That's compared to their simulation scan, and a clinician will determine whether there's been any significant change that will invalidate the plan. If the plan does need rework, we have to go all the way back to simulation and run this whole process again. And that has to happen in the middle of the patient's treatment. This diagram shows the same workflow. It's got a little bit more detail around the approval sections, but it's exactly the same everywhere else. This diagram is aiming to demonstrate where there are bottlenecks in our process. So on the x-axis, we have the time taken, with wider blocks taking longer and having more variation in the time they take. And on the y-axis, shows the variation in the output of a task. So taller blocks are more variable, possibly something that's subjective. We can see that the contouring and contouring approval steps take a long time. In fact, in this diagram, these 2 steps represent almost half the time between the decision to treat and the treatment starting. There are 2 key things that cause this: the efficiency of drawing the contours and their accuracy and variability. The contouring is often performed manually. A clinician will go through the CT slice by slice, contour every organ of interest. And this can be a time-consuming process, especially for complex areas with a large number of organs like the head and neck, which can take more than an hour to contour all of the relevant structures. There are auto-contouring solutions that don't use machine learning, but the quality that comes out of them is a bit hit and miss. Sometimes they're very good, other times they're very poor, and actually the contour just needs redrawing. So the amount of time they save is a bit variable. The second challenge in contouring is that we see significant variation in where clinicians will draw contours. So here's an example of the heart has been contoured by 3 different people, and you can see that there's a significant difference in where they've drawn it. This is what we call inter-observer variation, variation between observers. The variation can come from the training that the clinician has had. It could be preference of the hospital, or it could be that they're adhering to a certain standard, or it could be that what they're contouring is simply very difficult to see, and they've made a different judgment to someone else. We do also see variation in contours drawn by the same clinician. If they're asked to contour the same scan multiple times, perhaps a few days apart, and that's what we call intra-observer variation, variation between the same observer. So because contours directly affect our treatment plan, this variation directly affects the outcome of the patient. If an organ at risk contour is too small, that organ could receive an intolerable dose. If the contour is too large, we could be unnecessarily reducing the dose given to the tumour, and so making our treatment less effective. Some studies have shown that the effect of the variation in contouring is as significant as the effect of a patient moving during their treatment. Variation in contouring also leads to further delays when the contours are reviewed, as there's a disagreement between the clinicians and they need to go back and be altered and redrawn. So improving the speed of contouring reduces the width of our first box, the orange one, and improving the variability reduces the height of the first box and subsequently reduces the width of the second one. So overall, improving the speed and variability of contours results in a significant reduction in the time taken between treatment selection and treatment starting. Improving efficiency and variability in contouring therefore has the potential to improve patient outcomes, both by reducing the time to treat, preventing the cancer spreading and making the treatment more effective, and ensuring that they get consistent and accurate treatment, meaning it's more effective and the side effects are reduced. In the previous slides, I've given an idea of how contouring works and shown that it's basically taking a picture of the patient scan and identifying areas in that image. So really, it's just an image recognition task, which means it's ideally suited to being solved by AI, specifically by deep learning. And this brings me nicely on to DLCExpert, which is Mirada's deep learning contouring solution. In this section, I'll talk about how deep learning contouring works. I'll talk about how well it works and how we're currently using it. So as I mentioned earlier, deep learning is a subset of machine learning. It was first used for image recognition in the 1980s, but really took off in the early 2010s when GPUs were used, which allows the use of more complex architectures, and it allows more training data. Deep learning works in layers to create a hierarchy of features in our data, which it brings together to classify the image. So for example, given an image of a bicycle, the first layer in our network might identify a number of lines and 2 circles. The next layer might then realize that some of those lines cross over and that they exist in the middle of a circle, and so it deduces that that's a wheel. It might then also see that some of the lines come together in the form of a frame, and that one of them is at 90 degrees to the others, and deduce that that's handlebars. The final layer can then put that together, 2 wheels, a frame, handlebars, puts that together and deduces that the image is a bicycle. This is what we mean by our hierarchy of features. We get more complex and more like the image we're looking for, the higher up we go. The deep learning is based on neural networks which mimic the neural networks present in the human brain. Biological neuron is an electrically excitable cell which sends a signal when its input reaches a certain level. In deep learning, we have artificial copies of this, which were originally called perceptrons when they were first proposed in 1958. The artificial neuron accepts a number of inputs. Here they're x1 to x3. It applies an input weighting to each of these, w1 to w3. It then sums the result and performs some non-linear function on them and provides an output. Modelling has shown that this is equivalent to our biological neuron firing when the input reaches a certain threshold. So an artificial neural network is made up of a number of these artificial neurons connected together. So here on the left, I have a blue layer, which is our input layer. This could be, this is where we place our data, so it could be the pixels in an image or some text, whatever it is you're trying to classify. On the right-hand side, I have a red node, and this is the output. This is the result that we see, such as the classification of the image. Between them is a yellow hidden layer. This is hidden because we don't see what it does. We just see it contributes to the output, and we just see the output. So we don't actually see what the hidden layer is doing. Between the neurons, there are connections, here shown as the black lines. The connections provide the weights that we saw being applied to the inputs of the artificial neuron. And these are all tunable, so we can adjust the weighting that's given. In deep learning, we use a number of hidden layers stacked together to create depth and hence a deep neural network. The task of this network is to take an input and provide a prediction based on that input for the thing that we're looking for. So for example, if we're asking it to recognize an image, each of the red neurons on the right represents the possible answers that we're looking for. A dog, cat, horse. One for each of these. We apply an image to the input layer, with each neuron representing a pixel in the data. The connections to the first hidden layer apply a weighting, and then the hidden layer aggregates the inputs, applies the nonlinear function, and produces a value which is then sent onto the second layer via another weighted connection. It works through the network, going through all the connections and all the neurons, until finally the output neurons have a value, and that value is our prediction. So for example, if this node is labeled cat, and it's given a 0.99 value once we have gone through the network, then it's the network telling us that it's 99% sure that this is an image of a cat. To make the prediction useful and valuable, we adjust the weights that are applied by each of the connections until the network is able to predict with the accuracy that we're looking for. And this is what we call training. So when we're training our network, we first create a neural network and provide it with some random weights just to get it started. We then provide it with some input data. And this is known input data, so it's labeled, but we don't provide the network with the labels, we just provide it with the data. We then ask it to make a prediction. And we look at the prediction that it's given and compare it to what we know the answer should have been using the labels that we had at the start. We look at the difference between the prediction and the actual output, and then go back and update the weights in the network to improve the prediction. We then provide it with the data again, ask it to make the prediction, compare the output, and update the parameters. And we keep going through this cycle until the prediction isn't able to improve any further. We've hit a sort of convergence, it's called. We then want to test our network. So we provide it with some new unseen data. Again, it's labeled data, but we don't provide the labels to the network. It makes a prediction. We compare the prediction to the expected output. And if the network's able to predict the new data accurately as we like it to, then we say it's trained and ready to use. So looking specifically at image recognition, most images are very large. The scan of the thoracic region that I showed you could be several hundreds of megabytes large. If we apply this to the sort of network we've just been looking at with the colored neurons, we would have a very large input layer where each neuron is a pixel, so we end up with 400 megapixels, mega neurons essentially. So we end up with a very large input layer and then very large hidden layers and so many parameters between them that it's too computationally complex to tune them all. It becomes too computationally difficult to actually train that network. Fortunately, images have a structure which we're able to exploit, and we do this using a special type of neural network called a convolutional neural network. Convolution is an image processing technique. It's used all over image processing. If you have anything on your phone or your computer that does something like smoothing or sharpening, then that will be using probably some sort of convolution. The convolution features a moving kernel, which is used to perform a matrix multiplication. So in this little animation, our image is at the back. This is our convolutional kernel, and then this is our output. As it's moving across, at each step, the 9 pixels that are highlighted are multiplied with the convolutional kernel to produce the output value. We can tune the values of the kernel according to the feature that we want to pull out of the image. So one of the things that we can do is edge detection, which is what's shown in this lower picture. This is a convolution that's been performed with the kernel set to have values that specifically pick out the edges in the image. So in this picture of the cat, you can see that the output here has highlighted strongly with the bright color the edge of the cat, and it's also picked out the butterfly. It's also somewhat picked out the markings of the cat because there are stripes, which are edges, but they're not as strong as the edge around the outside of the cat. So this is an example of a convolution being used to create a feature map. We've applied a convolution, and what we've got out is a map of where the edges are in our image. The convolutional neural network performs a sequence of these convolutions to create feature maps that at each level, the feature is increasingly high level. This is an example of how it could be used for facial recognition. You start with some raw data, just pixel values. The first layer picks out edges. The next puts those edges together into facial features. And then the next layer puts all those features together into faces. So convolutional neural nets are used to classify images as a whole into a set of categories. And this is an example of the architecture. So the input is passed through a number of layers. So like this, where each layer is a convolution, a rectified linear unit, which is shortened to ReLU, and a pooling. The convolution is what we just discussed, where we're picking features out of the image. The box here is shown to go from a large to a small because the convolution reduces the size of the area. In the little animation, we saw the image was large and the convolutional kernel was small, and it was always applied within the image, which results in the feature map being a smaller resolution than the original image. The rectified linear unit provides the non-linearity that we see in biological neural networks, biological neurons in fact. It essentially clamps the values from the convolution to a minimum of 0, preventing the weights and the values in the neurons going off to incredibly negative values, which aren't helpful and just basically a drain on the computational power. Pooling reduces the size of the feature map by combining groups of features together. And often you would take maybe a set of 4 pixels in the feature map and take the maximum value, and then the image is a quarter of the size that it was. This is also done to reduce the amount of parameters and so it reduces the computational complexity of the network and making it more efficient to train. So on the left-hand side of this image, the data is all presented as three-dimensional matrices. Once we've completed our convolutional layers, the next thing to do is to flatten that into a one-dimensional vector. It's just a list of values. We take all of the values out of our matrix and put them into a one-dimensional list. We then use a fully connected layer, which is just like the blue, yellow, and red networks I was showing earlier. And that fully connected network is used to classify the image according to one of the categories that we've chosen. So here, car, truck, van, and bicycle. When we're training this network, we're adjusting the values in the convolutional kernels to teach the network what features it should be looking for. And then we're training the weights in the fully connected network to teach the network how to classify those features into the classes that we're looking for. Now, because we do this flattening of our feature map into a vector, the fully connected layer is only able to predict the image as a whole. So there is no spatial information in our vector. There is no localization. So all it's able to do is take all of the values and pick one output classification and say this image is one of these things. And while that's a useful skill, it's not really what we're looking for autocontouring. We want to be able to take our image and pick out multiple different organs on the same image. So a simple convolutional neural network doesn't quite fulfill our needs. And that's where we get a fully convolutional neural network. So on the left of this image is the same as the convolutional neural net from the previous slide, just before the point where it flattens into a vector. So on here, on the left-hand side. We call this part our contracting path because the resolution of the feature map is contracting towards the center. On the right-hand side, we have our expanding path, which is a mirror image of the contracting path and takes a low resolution feature map and returns it to the resolution of the original image using deconvolution. Deconvolution is much the same as convolution. It's the same process, but the kernel is either larger than the image or it's placed such that it goes outside the resolution of the image, which increases the resolution of the output compared to the input. So once we've returned to the resolution of the original image, we end up with a heat map of each classification that we're looking for that shows where it's most likely to be. So here they're obviously looking for one class, which is the bicycle and the background. And it's highlighted that this area here is where the bicycle is most likely to be. There's a bit of a spurious prediction here, but it's most sure about this area of the image, which corresponds nicely with where the bike is in our original. In this network, there's no fully connected layer, so the only thing to train is the convolutional kernels at all steps, both on the contracting path and on the expanding path. So we're training it on which features to pick out, how to expand them back to the original resolution, and then how they correspond to each of the classifications. This is exactly what we use for deep learning contouring. We specifically use an architecture called a UNet, which is popular and very successful for image segmentation. Each category the network is searching for is one of our organs at risk, and the output of the network is a map of pixels and which category each pixel is most likely to be in. And we then turn that into our segmentation map. So how good is DLC? Let's think back to what we're aiming to do. We want to improve patient outcomes by reducing the time taken to draw contours and to reduce the variation in those contours. We're aiming to help humans and not replace them. And that gives us three challenges. We want to create contours that are as good as a human would draw and to make them consistent. We want to create contours which are acceptable to humans so they don't have to rework them. and we want to draw those contours faster than a human would. So to explore the first two questions, Mirada created a Turing test. A Turing test is an imitation game designed by Alan Turing to determine whether an AI is capable of human thought. In the original game, a human converses with an AI. If the person believes they're talking to a human, then the game is won. If the AI is detected as an AI, the game is lost. So we created a Turing test website that shows the player a contour and invites them to decide whether it was drawn by a human or a computer. Some pages of the website also ask them whether the contour is clinically acceptable. And we also have a game where the website will show a contour drawn by the computer and one by the human and ask the user which they prefer. So starting with the results of our identification test. In a test like this, you're looking for the users to get half of the questions right and half of them wrong. This indicates that they don't really know the difference, they can't see the difference, and their right and wrong answers are purely down to chance. If you don't know the difference, statistically speaking, with a large number of people, a large number of goes, if nobody can tell the difference, you'll end up with a 50-50 split between correct and incorrect answers as people make guesses. So in this chart, the red bars and pies represent incorrect answers, and the blue indicate correct answers. And these are the results of a scan in the thoracic region with 6 contours. We can see that roughly half of the answers are correct and roughly half of them are incorrect. There is a slight bias towards correctness. We believe that's because users noticed that some contours are smoother than others, and then they correctly deduce that the computer has drawn the smooth ones. But regardless, it's an indication that generally users can't tell the difference just by looking at a contour, whether it was drawn by a human, which is an indication that DLCExpert can draw contours that are as good as a human. So we next look at the preference test. Here, the blue side of the pie chart is the deep learning contours and the red side is the humans. And we're showing the number of each that was chosen to be preferred. We can see that they are almost equally preferred, but there is a slight preference for humans, which is another indication that our deep learning contours are roughly the same as what a human would produce and are about as good as a human's. And then finally, we look at clinical acceptability. So in this, we displayed a contour to the experienced clinicians and asked them whether it would be accepted or rejected for use in a treatment plan. In this chart, on the right-hand side are the human contours, and on the left are the deep learning contours. The orange bars are contours that are accepted as they are for use in a clinical treatment workflow. And then the blue ones are rejected, and they may need either minor rework or sort of completely redrawing. We can see from this that quite clearly the clinicians accept and reject the deep learning contours at the same rate as the human drawn contours. This is a very good indication that the contours drawn by DLC are as good as a human would draw. So these 3 tests have shown that the contours produced by DLC are as good as a human and they are acceptable to humans. Because we're drawing them programmatically, we know that they'll be more consistent. Every time DLC is presented with the same scan, it will produce the same contours. We can also train the network using contours that were drawn according to a certain standard and know that all the contours produced will adhere to that standard, providing consistent treatment across clinics so that a patient can be treated at any clinic, by any clinician, at any time, and get the same standard of contours. This chart also shows an important part of the education around DLC that I mentioned earlier in the webinar. Deep learning contours are not perfect, but they are as good as the human. In both cases, about 30% of the contours were rejected for rework. But the difference in these 2 cases is the timing, how much human time was needed in each of these scenarios. So on the right-hand side, 70% of the contours were drawn by a human and accepted, and 30% of the contours were drawn by a human, rejected, and then reworked by a human. On the left-hand side, 70% of the contours were drawn by the computer and accepted, and 30% were drawn by the computer, rejected, and then reworked by a human. There's a significant difference between these two scenarios of how much time is needed by the human clinicians. And this is reflected in our own time-saving experiments. So we ran a study in collaboration with the Radiotherapy Centre in the Netherlands, looking at evaluating deep learning contours for use in the thoracic region again. So in this study, the scans were contoured by DLCExpert and by a human, and they were then reviewed and edited. The total time taken to do the whole task was measured. We measured the whole time because it tells us the overall length of the contouring process. There's no point drawing contours quickly if they all need to be redrawn after review. So the thoracic region has, in this case, had 6 structures being drawn, and it's also traditionally one of the fastest areas to contour manually. So in this chart, we have time across the bottom. We can see that manual contouring took on average 21 minutes, while DLCExpert took on average 9 minutes to complete all of the contours on the scan. That's an average of 60% time saving per patient, and that's pretty successful. Deep learning contouring reduces the time required for contouring while consistently achieving the quality we expect from a human. So deep learning contouring allows us to reduce the time to treat a patient, meaning that the cancer has less time to spread and is more treatable. We're treating accurately, meaning the patient has minimal side effects and the treatment is as effective as it can be. And we can provide that consistently so that no matter where they are treated or who buy, they get the same quality of care. So our software, DLCExpert, received FDA clearance and a CE mark in 2018, meaning it can be used across Europe and America, and we're also cleared for use in Japan. It's sold as part of our WorkflowBox product, which is an automation platform. WorkflowBox provides a zero-click experience, so the clinic can set up a system to receive scans straight from the scanner. All they have to do then is scan the patient, and the scan is automatically sent to DLCExpert for contouring, which then sends it on, and it's available as soon as someone sits down to review it. And all anyone at the clinic has to do is scan the patient. We have models available covering the head and neck, breast, prostate, and thorax, which are the most common treatment areas. And clinics can choose to commission a model to be trained using their own data, or they can use one of the models we've created in-house at Mirada. Use of DLCExpert is growing rapidly, and we're predicting that in 2021, this year, at least 25,000 treatment plans will be created using DLCExpert to draw the contours. That's 25,000 people whose treatment will be improved by using AI to create faster and more consistent contours. Thank you very much for listening.
Thank you so much. We really enjoyed the talk, and I'm now inviting people to ask any questions you would like from Lottie. You can type your questions up in the box provided in the webinar. I will read them out and then I'll ask Lottie to give us an answer. Now, if we do run out of time, what Lottie's kindly done is provided her with her contact details, so you can always email her too. So when you're ready, do type up your questions. Thank you, Lottie. It was an amazing talk. I really enjoyed it myself. So much information that I didn't know about, and I do. Just waiting to see if there's any questions. It's amazing how many people have actually got this, your application installed. It's quite reassuring, and it shocked me how many people are waiting for treatment in cancer. It's yeah, it's amazing, because you'd think that, in fact, we're kind of on top of things more as time has gone by, but it doesn't feel like that.
Yes, there's a very interesting study in the Lancet. It was released on Monday, actually, looking at how many people are in the backlog, how many people didn't come forwards for investigation, and it's quite stark. It's amazing to see kind of the impact of something like COVID on cancer treatment, and how much it might put us back in the advances that we've made over the past few years.
Yeah, definitely. Lovely. So somebody has said, I don't know if I can see all the questions actually. Let me just make sure I can expand on this. Right, 1 second. Let me just, yes, I can see them now. Lovely. So the first question I have is from Marcin. Thank you, Marcin. And they've said, thank you for the talk, nice talk. Where are the data stored? Is it in cloud? And I think that's, yeah, that's the first question. Thank you.
So for DLCExpert and WorkflowBox is a completely on-premises solution. So the data is only stored at the hospital site. For obvious GDPR reasons, cloud is a little bit tricky in hospitals. We've got patient data, that's clearly personal data. And so implementing a cloud solution is quite tricky. So our WorkflowBox is completely on premises. The data never leaves the hospital site.
Makes it more secure, doesn't it, really? The second question I've got is from Hugh. Thank you, Hugh. Are you able to use artificial intelligence to delegate, I think that's delegate, the target, the cancer itself in the planning process? Does that make any sense? Sorry, I might have to read that again. Are you able to use AI to, I think it's delegate the target, the cancer itself in the planning process? Hugh might need to just, can you write that question again a bit more clearly so I can read it out? Sorry.
I suspect it's delineate, which is another word for the outlining of the contouring process.
Okay, sorry. So, word I didn't know. There you go.
So yes, certainly delineating tumours is something that is definitely of interest. Contouring a tumour is one of the things that takes longer, because it's sort of the tricky part, because it's the bit that you need to have a lot of review on. It's usually the oncologist that does the contouring of the tumour, whereas organs at risk can be done by a number of professions. The tumour needs to be done by the oncologist, whose time is more expensive and often more restricted. So using AI to delineate the tumour is definitely something that we'd like to be able to do. It is slightly more tricky in terms of the regulatory side, because it's a slightly higher risk, which is how the regulators kind of describe when I talked about the levels of evidence, where something can be very basic or very complex, the level of risk is what determines how much evidence you have to provide. So tumour delineation is slightly more complicated, but it's definitely something we would like to be looking at doing.
Thank you so much. So next question is from Keith. He says, thank you. How much effort was it required to obtain the CE, that's C for Charlie, E for Edward, marking? Was any recording required? That's from Keith.
So DLCExpert is actually a minor level of concern. So it's quite a low risk product, because it's drawing contours which are going to be reviewed by a clinician. It's not making any decision for itself, and everything that it does is reviewed and approved and could be reworked. So obviously it's not an easy process going through submission. You have to show that it's effective and that it's correct, everything I talked about. But in terms of the amount of evidence, if you compare it to something like the COVID vaccines, it's nowhere near that level of evidence required for something that's going to be reviewed like DLCExpert.
Lovely, thank you very much. Next question is from David. David's asked, how well does it cope if there is a developmental variation in the structure or the variation following previous treatment or, say, an accident? Thanks, Lottie.
Yeah, so this is one of the areas that deep learning can struggle. So sometimes we'll see maybe patients with collapsed lungs in the thoracic region, maybe pacemakers, maybe they've had, breast patients will have had surgery on one side. So deep learning can struggle in those cases, and what we would be trying to do is making sure that when we train our network, we have a sufficiently varied data set that includes enough people. So pacemakers are quite common. We have plenty of people in our data set that has a pacemaker, so that the network is able to understand that when it goes to do a new prediction.
That's pretty useful, isn't it? And then next question is from Kate. Thank you. My experience in radiotherapy is that we significantly change algorithms. We have to resubmit our regulatory evidence. How is that handled if artificial intelligence changes these on the fly? Thanks. And she also says, thank you so much, a great talk. Yeah, thank you.
So I guess one thing is that DLCExpert doesn't do any learning on the fly, so it's trained and we produce a model, and that's that. We don't do any more learning once the model has been trained, unless the clinic requests a retrain, in which case it would come back to us and we do a nod training and they'd get something else that's fixed.
Lovely, thank you. Thanks. Thank you. Did you want to say any more about that? Are you okay? Should I keep going?
No, I think I mentioned the talk. The way to handle continuous learning is to, as you said, as the person who asked the question said, is to do retesting and retrials. And obviously, we at Mirada, we appreciate that that's quite a burden, and it can be quite a burden for clinics to accept updated software and prove that it's effective. And so we don't do continuous learning to avoid that kind of process.
Perfect. Okay, so the next question is from Chris. Chris is asking, what machine learning libraries do you use? Probably in Mirada.
So we use TensorFlow as the backend for our machine learning.
Lovely.
I hope that answers the question.
Oh, yeah, that's a great question. Brian has asked a question as well. When you create a contour, which is not acceptable, can you find out why it came up with that proposal? So kind of going back and, I guess, troubleshooting it, isn't it?
So this is quite challenging to do with deep learning. Because of all the hidden layers, you really only see the output, and it's quite hard to, there's no placing a breakpoint and asking, what are you thinking at this point? It's a black box. Sometimes you can see why it's done something. For example, in that previous question, where the patient is significantly different to what it was trained on, you can have a suspicion that maybe that's what's confused it. But there's not really any way to sort of query the model and find out why it's made a certain prediction.
Lovely, thank you. Next question is from Thomas. Thomas says, thank you for the talk. Do you ever see this solution going further than just contouring and actually making medical judgment without human intervention, for example, diagnostics and treatment suggestions? So like in the kind of future, what would happen?
I certainly think it's a way that we're going. There's certainly a definite interest, not so rather, there's certainly a definite interest in using AI to make treatment decisions and to help reduce the burden. As I keep coming back to the regulatory, the more that you claim your software is going to do, and the further away you get from having a human to hold its hand, the more hard work it becomes to prove it does what you say it does. One of the things we've been working on at Mirada recently through a grant, because we have our science team work on a number of grant projects, is to look at the scenario I said where the treatment plan needs to be changed during treatment because the patient anatomy has changed. One of our grants is looking at using an AI assistant to tell when the the plan needs to be changed. So instead of having to have a clinician review and say that that's significantly changed and no longer viable, that's one of the things that our science team has been looking at. And so that's starting to move into making clinical judgments. It's something that's kind of quite in our prototype stage at the moment, though.
Lovely. Thank you. It's amazing how, you know, if the body changes, then the treatment has to change. I didn't think about that previous to your talk, actually. The next question is from Chris. Chris is asking, what languages, I guess that's programming languages, and frameworks would you be using, possibly Mirada, I guess?
So the majority of our applications are written in Java, and then we have C++ is used for anything that we need to go particularly quickly. So we do a lot of image processing, as well as our deep learning. We do image processing, that's all done in C++. And our science team predominantly use Python, so Python and MATLAB, actually.
Lovely. Yeah, I know about Python. Keith said, thank you very much for the answer to the question you gave earlier. Thank you. And then the next question is from Marcin. Do you think you will be able to optimize the radiation dose based on the outcomes? And or maybe the radiation dose is already well known? So that's Marcin's question. Don't know if you can answer that. Don't worry if you can't, if you've got to come back to something.
So the radiation dose is normally done sort of standard treatments, maybe for breast cancer of a certain type. They'll have a good idea based on clinical trials what dose is required to treat that cancer. Where it gets quite interesting is how different people respond to the treatment. So some people, the tumour might reduce faster than others. Some people it might not reduce so fast. When the tumour reduces quicker, you might end up over-treating. And if it reduces slower than expected, you might want to boost your treatment. So something that some clinics are looking at is what they call dose of the day, treatment of the day, where every day that the patient comes in, they will slightly adjust the plan to make sure that what they're giving is exactly right for the patient on that precise day. And that's somewhere that something like DLCExpert is going to become really helpful, because it can redraw those contours really quickly. It's a 60% saving per patient. Lets them get the patient in, scan them, redraw the contours, replan, and give them an exactly precise dose for that day.
Gosh, that's a very detailed answer. Thank you. It's amazing. You've got an amazing knowledge there. Thank you. I don't think there's any more questions. I just want to say thank you so much for doing this talk for us, and we are recording this talk, so if you need to just go back, or if you want to recommend for people to watch the talk again, then certainly we'll put it on our website. We have like a library on our website which you can access. You just go to BCS Oxfordshire, and then you can then search for the library and talks that are recorded. It will take us a little while to get the talk ready for you, so do let people know if they want to hear the talk again. Also, Marcin has said a very nice talk, Lottie. So there we go. Lots of positive kind of feedback there. Thank you so much. So I've just want to kind of work out how to unmute everyone to clap. So I'm going to have to, I don't know if my colleague is going to do that for me, Simon. Simon, can you unmute everyone so they can clap? Yeah, thank you. Thank you. If you can unmute everybody so they can have a go at clapping. Is that all right? And then we can say final thank yous.
Right. Yeah. What are we doing? It doesn't seem to. I'm not sure I can do it.
Oh, okay, don't worry, don't worry.
You'll clap on everybody's behalf, I think, Ginnis.
Yeah, okay. Thank you so much, Lottie. Thank you. So thank you so much, Lottie. thank you for being here and doing this talk. We really appreciate it. It's just amazing technology, and I think there's so much more to learn that we do not know at the moment, and I think it's evolving. And you yourself are so young, and I think you're going to be a generation who's going to evolve artificial intelligence in our future, and we're going to see it in hospitals, and we can see it improving our health. And in a way, our health is the most important thing. We wouldn't be here if it wasn't for our health. So this is kind of integral to our life and lifestyles. So I've got, Margaret has said, thank you, very interesting talk. And Marcin has said, very nice, Lottie. And Marcin also said, thank you. So there we go. So thank you, everyone. And thank you, Lottie. And thank you to Simon to support me through the talk. And yeah, we hope to see you next month for our next talk. And Lottie, thank you, you're amazing. Take care. Okay, and everyone's saying very interesting and thanks. David said thank you. Chris is saying thank you, very interesting, so lovely. And if you haven't had a chance to ask any questions and you have thought about it at a later date, then do, and Lottie's very kindly provided her details, do contact her by email, and that would be the best thing to do. And I will say good night to you all. Have a lovely evening, everyone. And I'm now going to stop the webinar. Okay, thank you. All the best. Bye. Bye, Lottie. Thank you. Bye, Simon. Bye, everyone.
Bye.